Welcome back, BC students. Mr. Record here from Avon High School, and we're going to take a look at our third and final video over probably one of the most difficult topics in all of AP Calc BC or Calc 2, the Lagrange error bound. And I want to give you a big bravo so far. If you've really fought through examples 1 and 2, you start to develop an understanding, you've done pretty well. Hang in there, see if you can understand a little bit more about the components of this particular problem. It's got a lot of different moving parts to it, and that's just going to get you closer to really mastering this idea. So let's take a look at our example here. Move my camera down here for the time being, and it says determine the degree of the Taylor polynomial Pn of x that's expanded about c equal 1 that should be used to approximate the natural log of 1.2 so that the error is less than 0.001. In a nutshell, we want to know how big does this polynomial have to be so that when we plug in our desired x, that's going to give us an approximation of natural log of 1.2, so that we're only 1,000th away from the actual answer of the natural log of 1.2. So where do we start? Well, one of the things that I would suggest is to get an understanding of what's happening is we know that our function f of x is certainly going to be equivalent to the natural log of x. So no worries there, right? What we don't know yet is what is our Taylor polynomial for the natural log of x. Sure, we could compute it. We could go through the process of finding all of these derivatives and evaluating them at 1 and building the polynomial. But I want to do a little bit more with this video than just that, and I don't want it to be so long. So if you recall, at the end of topic 1011, we have this green table that listed our 5 of our most popular polynomials, at least out to 3 terms, and that's what we see here. So I could say that the natural log of x is equivalent to x minus 1 minus x minus 1 quantity squared all over 2 plus x minus 1 quantity cubed all over 3. And I tell you what, why don't you give me one more term just so that you can notice the pattern. Hopefully you all see it. That's a minus x minus 1 to the 4th over 4. And in order for me to really pull off putting an equal sign here, I probably should put a dot, dot, dot here to indicate that this will go on forever. And that's the only way that we can really equate the natural log with the Taylor's polynomial, is if it was an infinite polynomial or an infinite series. And we're going to talk more about the series aspect as we move into the last 3 topics of Unit 10. Well, okay, where do we go from here, you might say? Well, I do know this. One thing that we're going to have to consider, and I might as well bring it up right now. If we were going to approximate the natural log of 1.2, one thing that you have to realize is that we would plug 1.2 in for all of these x's, right? And so I could say that the approximation would be what I get when I plug 1.2 in and I subtract, so that would be 0.2, of course, and plug in another 1.2 in and I'd have this. And you guys pretty much know the trick, right? And I'm not going to worry about computing this because I don't really know how far to go with it, right? So if I stop at the 4th term, I know that that could serve as approximation. Is it a good enough one that puts me within 1,000th? We're going to find that out. And the way that we're going to find that out is to use the contents of the orange box. We have to use Taylor's inequality. It says the absolute value of Rn, which is our error, is essentially less than or equal to the absolute value of the maximum of the nth plus 1 derivative of our function f, evaluated at some z, where z would likely lie between c and x, which would be between 1 and 1.2. And then we have our n plus 1 factorial on the bottom and our x minus 1 to the n plus 1 power. And we want that expression. That's the expression right here. That's the guy that's got to be less than 0.001 eventually. But we have a problem here. finding this nth plus 1 derivative is what is going to be a bit of a challenge, I believe. We're going to have to very carefully compute a few of these derivatives so that we can come up with some kind of a pattern. And because we weren't forced to do that to develop the polynomial in the first place, I kind of feel like I'm working backwards here, because this may have likely been already something that you would have put on paper if you didn't have that memorized. But this won't be too bad. Let's go ahead and take several derivatives of natural log of x and see where it takes us. So the first derivative is, of course, 1 over x. And the second derivative, hopefully you can all tell from this, would be negative 1 over x squared. Things are going to start to get a bit interesting now when we get to the third derivative, because x to the negative 2 is how we would rewrite 1 over x squared. With a negative already in front, we're going to get a positive, but I think we're going to get a 2 coefficient, x to the negative 3, so we could write that as 2 over x cubed. If we continue for the fourth derivative, we're going to go back to the negative number world, and then we're going to end up with 2 times 3, which is 6, and that's going to be over x to the fourth. Let's go ahead and take a fifth derivative. Doing so would give us positive 6 times 4, 24 over x to the fifth. And I think you can start to see a pattern develop with these numerators. 1, 2, 6, 24. They all happen to be factorial values. Hopefully that's kind of obvious, because what we're going to do now, or at least try to do, is find out what is a nth derivative formula for our function. So if we give that a shot here, what we're going to notice eventually is that each term is a fraction. Okay, check. We're also going to notice that the numerator is always some kind of a factorial. We're also going to notice that each term is alternating, and we're going to notice that x in the bottom is just being gradually raised to a power. So let's take a look at each of those individually. How about the alternating piece? By now you should know that an alternating operation looks something like negative 1 to a power. We just have to choose the right power. Is it n plus 1, or n minus 1? Well, seeing as how the odd derivatives, 1, 3, and 5, are giving us a positive result, I think we're going to have an n or an n minus 1 here. And it really doesn't matter. You're going to find out I could use an n plus 1 and it's all the same. I'll use an n minus 1 in this case to ensure that I get that even exponent when I put an odd number for n. That way the negative goes away. And then in addition to that, hopefully you see that if the numerator is going to move from a 1 to a 1 to a 2 to a 6, I think what's really happening here is that in relation to the factorial, I'm sorry, how about the exponent, or the derivative, I should say. Let's use the word derivative. In relation to the derivative, 3, 4, 5 over here, the numerator is a factorial value that's 1 less. Let's test that. 3 here, 3 minus 1, or 2 factorial. A 4 here, 4 minus 1, which is 3, factorial. A 5 here, 5 minus 1, or 4 factorial. So we could actually write n minus 1 factorial and have our numerator. And if you're wondering, oh, does that work over here? It does, even for this 1, because 1 minus 1 is 0. 0 factorial is 1. Remember, it's defined in probability. How many different ways can you put 0 books on a shelf? One way, an empty shelf. Now, if we take a look at the denominator, we're going to get x to the n. All right, so what do we do with this? Well, what you're going to do is you're going to evaluate this at 1. That's eventually one of our goals, to figure out exactly what our coefficients are going to be. And when you evaluate this at 1, and furthermore, I'm going to have us start thinking about using absolute values. Now you might think, wait a minute, we didn't do that before. Well, since absolute values are going to be wrapped around our nth plus 1 derivative expression, we might as well start thinking that right now with our nth derivative expression. And so essentially what will happen is if I put absolute values around this right side, the negative 1 to the n minus 1 component goes away. X being 1 all the time, 1 to the n is not going to be significant. And so basically you have n minus 1 factorial. Not too bad, right? Well, what does that mean? Well, that means if we take the nth plus 1 derivative evaluated at 1, then we're just going to take this n and raise it up a notch, a value, and therefore we'll have n factorial. Now, let's see how we can make this work over here. So where are we? Well, we're at a stage here where we want to compute the absolute value of the nth term of r at an x we know to be 1.2. Because remember, this is our error. Sometimes it's called remainder, sometimes it's called error. It's the specific error when we evaluate at that specific x. So according to our formula, this is less than or equal to the absolute value of the maximum of the nth plus 1 derivative of f evaluated at, z, okay, we'll deal with that in a second, all over n plus 1 factorial times x minus c. Now, remember a couple of things here. Your x is 1.2. Your c is 1. All right. We knew that c was 1 because it says we're expanding about c equal 1. And since we're evaluating at 1.2, certainly that's going to be our x. Okay, so where does this take us, you might ask? Well, if we look at this a little bit more in depth, we find here that the nth plus 1 derivative evaluated at this z that we'll never seemingly know is going to be a bit problematic. So what we're going to do is we can use this value in factorial there. Now, why is that the case? How do we know that that would be necessarily the largest value? Is that truly going to be the maximum value, in other words? So why is it that we can say that the maximum value of the nth plus 1 derivative at some z that we can't determine is our n factorial, which is what we had down here? Well, you guys, it all kind of deals with the fact that by the time you start looking at any one of these highlighted functions, disregard the negative because we're living in the world of absolute values. You have a decreasing function. Every one of these will decrease on the interval 1 to infinity, let alone 1 to 1.2. As x gets bigger, the fraction is going to get smaller. And so the only way that we can achieve the maximum is by starting at the very left of that interval. Remember what we said about z lying between x and c. In this case, my c is 1, my x is 1.2. There's where this z should live. And you can see that if we let z be the left end of that interval on a decreasing type of function, we're going to get our max. So that's why we use this n factorial. Now the rest of this follows suit pretty logically. You have an n plus 1 factorial there, and then of course a 0.2 to the n plus 1 here. And that should all be less than the error that they provide of 0.001. Let's go ahead and do a little bit of simplifying. N factorial over n plus 1 factorial, we know to be n plus 1, of course. I'm going to do a little bit of maneuvering here with this 0.2, a little trick I'm going to show you. I don't like decimals. This is the same as 1/5, right? 0.2. Well, if you were to take that 1/5 and drop it into the denominator, it would just be a 5. And you can still attach the same power to him. How cool is that? So that's a nice little nifty trick that you can use. That makes this numerator a 1 since there's nothing else there, and we're still less than 0.001. Did I mention I didn't like fractions? So if we reciprocate the left side, basically flip it, we can reciprocate the right side. 0.001 is just 1,000, but you have to make sure that you also flip the inequality. That's really important there. And now you're at a point where, well, if we could solve this thing, we're in business. Problem is, this is a hard thing to solve. And so you might find yourself having to just go down the nice trial and error avenue. Let n equal 1. What's 2 times 5 to the second? Well, I don't know about you, but it's certainly not larger than 1,000, right? 50 is not going to work. So let's try n equal 2. 2 plus 1 is 3. 3 times 5 to the third. Well, I think we're getting closer, but this is like 125 times 3, which is 375. So we're still not there, but we're on our way. Now, if we let n be 3, we would get 4 times 5 to the fourth. Now, at this point, I don't think you'll have to completely calculate this. 5 to the fourth is just 5 squared twice. 25 times 25, that's 625. By the time you multiply 625 by 4, you're well over 1,000. So we know that this now becomes a true statement. And it's only true when n is equal to 3. And so that would be your answer. 3 terms will give you an approximation of the natural log of 1.2 that's only 1,000th off of the actual. Let's take a look and prove it via the calculator. So here we go. Now I've gone ahead and defined our third degree polynomial to save some time so that we can just simply evaluate that at 1.2. So let's make that happen. P3, I should say, there we go, of 1.2 gives us this answer. Well, okay, that's all fine and dandy. What about the actual value of the natural log of 1.2? Well, a calculator can spit that out in no time. And so I guess now what we're concerned about is let's take the absolute value of the difference between the polynomial and the actual. And since it doesn't matter which one that we enter because of the absolute values, I don't have to really worry about that too much. So I'll put in my approximation first, and then I'll subtract, and then I'll enter the actual value. Notice it's going to give me a lot more decimal places, which is fine. That's just more accuracy. Hey, we'll always take accuracy. And then if I hit enter and move my ugly mug, we end up with a value here that I think you and I will all agree is less than 0.001. Let's say that we would have stopped here at our second degree polynomial and evaluated that at 1.2. The difference between it and the actual value is not going to be this small, and probably indefinitely will be a number that's larger than 0.01. So we needed that third degree polynomial to make this work. So n equal 3. 3 examples obviously isn't enough to really show you all of the complexities that surround the Lagrange error estimate. Now's the time for you to seek out your particular resources for skill builders in my class. We also have an enrichment multiple choice. If you're watching the video outside of my school, your teacher is certainly going to provide lots of materials for which you to use and practice. In the grand scheme of things, is this all over the AP Calc BC exam? No, maybe 1 point, maybe 2 points total out of 108. That doesn't seem like a lot, but I don't want to concede points anywhere. If you're a BC calculus student, you want to be hungry and to try to get every bit of the points that are available. If you like this video, make sure you hit subscribe, smash that subscribe, and be sure to tune in for future videos. We're going to move on to 10.13, talking about intervals and radius of convergence for power series. We'll see you next time.